the solution will be, no, we will follow our process. We will follow our process. We will follow our. No, yeah. That's the reason. No. That's the reason.
Kann man?
The product is the services that we will deliver in a efficient way. The customers is only two outside of this. So we have to from the no, not yet. The question is this is our current product. No, we have it's the product. This is how it is right now. It's not the product. Yeah, not yet. But you need it. The question is, everyday life your requirement is what? To go from point A to point B. Yeah, that's a problem. The problem statement here is what? That's the problem. I know, but the question is, what do you start with? Maybe you get a fair price. Maybe from point A to point B, but you still want to go from point A to point B.
Ja.
I completely understand, but I don't even remember when this fair price comes here. This is what is defined. When we went about creating this, before the first thing came here about tax, fine tax, what was the problem with getting a transport, going from wherever we are, the hotel, the question is, how do we go? Let's get a taxi. Then after we decide, when we get a taxi, what are the key points of the job? That probably you know that for example there's like customer segments
Eine Frage, wie lange dauert der Vortrag und was ist das genaue Thema?
Artificial Intelligence, es geht um Machine Learning, Einführung,
Jetzt nachher die Folien auf.
muss ich fragen, aber theoretisch schon, ja.
Und Dauer?
20, eine halbe Stunde für das Studium. Gerne. Ja?
Machine Learning ist ein Top-Thema, also ich glaube auch, das
Ja.
einzubauen,
Ja.
zu gucken.
Cool. Mal los.
Wir bräuchten noch irgendwie so Whiteboards oder irgendwie ein bisschen interaktiver zu gestalten.
is our idea, where we have different messages that we play. Good. And actually, we didn't get any special the small that happened with my boss was at the end of the year, and she said, I will spend on my I need to get rid of 2,000 Yes. Just little bad snacks. How can I contact them? Because we have right now on one we have two. One is for secure transportation, which you will go in, make a reservation for a taxi. So only going to be authorized reservation. So I will go, for instance, I will make arrive to the airport. I will schedule my travel in advance. He will give me the secure drivers. So I can confirm it, depending on the availability. He will send me all the drivers' information, the card, the picture, because they're screened by us. But that's a different use case. That's transportation Vielleicht auch mal ganz gut jetzt mal. Imagine yourself going to Mexico. You don't want to pay in cash. I booked it and I know that
Go on your seats now. Yeah, just take your seat. Lemon.
Okay.
Next sugar. Not so much sugar. If you want, just grab your bread or your soup. It's fine. It's kind of a interactional dinner. So, what an exciting day. And if I picture myself standing here this morning, the kind of faces I was looking through faces right now, it's an amazing difference. So, what you made out of it, what you dared, what you collected, it's great. So, as promised, tomorrow you may unleash your problem solver, finally. And to accompany this, as mentioned, we have prepared 2 technology inspirations. The keyword here is inspiration. Again, don't expect that someone is telling you the solution you're desperately looking for. It's more like in the whodunit that you step back a bit, get a broader overview, and that you sharpen your attention and have other questions, that you detect possibilities and other combinations. And we have two distinct subjects today and tomorrow. Today is artificial intelligence, tomorrow is blockchain. And the idea is not just to describe in a technical way, in an expert way, what's happening there, but to give you an understanding about the context and what's driving the modern capabilities. So, with that in mind, I'm handing over to you guys. So, who's on stage today?
Right. So, thank you, Ingmar, that you join us today. I actually know Ingmar quite well during my time at Innowerf. Innowerf is an incubator in the Rhine-Neckar region, and Ingmar was working there as a customer development manager. I used the Innowerf basically as my co-working space, and in that time we had lots of good conversations, and I noticed that he's a real expert in AI and super passionate about this topic. Yeah, and he made it into reality, basically, his passion. Now he is CEO and founder of iMundo. iMundo is actually a claim assessment automation for crop insurance. Maybe you can explain it later on a little bit better. And he's also a data analyst at the Karlsruhe Institute of Technology. So, yeah, the stage is yours.
The first picture. All right. Yes, thank you. I'm looking forward to this talk, which is not going to be a talk, because I think the most you get out of such sessions is when you have a lot of direct and personal connection to it. And that is the reason why I put the word gentle there. It's not meant that I don't think you would be not capable of understanding what is behind this buzzword, artificial intelligence. We'll get to that in a moment. So, in the beginning, I want to tell you my journey very briefly, because it's very connected to startups. And then we will dive into those technical worlds with the aim of providing an intuition, an intuitive understanding of the capabilities and the constraints. So that is me already many years ago. So I did a lot of sales, like a direct customer contact. So I really know what you did today is amazing groundwork, cannot be underappreciated. I worked voluntarily in some student organizations like ISEC, where I had great team experiences. This also added to my way of learning about what matters. And I also engaged a lot in workshops and trainings and all of this. So this is also something I offered to teams to help them review how they actually behave, how they can unleash potential. I did that all while being a student, and this was the first product-oriented startup. I have a few pictures of this. It was basically an electronic menu, so we did the whole startup, bootstrap, and financing journey until in the end, so this is screenshots of the product, until in the end people could actually order with this device in restaurants. Then I was going a bit into fintech and also into a topic I'm passionate about, which is a mixture of like chat and forum, RSS feed, a little bit like this. All of those projects are not the focus right now. Right now, I work 50% as a data science research assistant at KIT. And this I'm doing because first it provides a steady money stream so I can cover my living expenses. it's also extremely helpful to me to have a mental challenge, which I use to grow, and it's obviously very relevant to a startup where you use artificial intelligence. So that's Heliopass AI. It used to be called AI Mundo, but yes, names change. And yes, what we do is when a farmer has a field and is unsure about the weather, because the weather is by nature unsure, maybe he wants to protect himself from damage. And if damage occurs, there is a lot of manual labor that happens. People have to go there, control it, assess the damages like that, and the farmer disagrees, a lot of paperwork. And we will do all of this automated with satellite images and a lot of other data. So what I learned in the startups is that there is no predictive way. That's why I like it so much, what I heard in this evening, that you start with the customer, with the needs, with the problems. And there is no definite knowledge. No startup ever would have known from the beginning what was the end. And in my understanding, this is what there is. Experience, pragmatism, and it's about making lots and lots of decisions under uncertainty, focus and fulfillment. So uncertainty, no predictive knowledge, all of this, it's very related to data science, which many people at first glimpse would not really think it is. So, is that actually a science, data science, what they do? Because in the end, what artificial intelligence intends to do is to mimic the human brain. And we all know from our own experience how often our own brain fails. We get things wrong, we can't remember stuff, we mix things up, we speak in the wrong way, we lose a lot of knowledge over time. And now we want to build computers with those disabilities. So this, per definition, can't be an exact science, but it's using a lot of exact science. And I want you, at the end of this session, to kind of have an understanding why this is necessary, and what the benefits of this approach are, and also, of course, its constraints. So the aim today, get the intuition of what data science is and of its limitations and potential. Who can answer this question to me? Just try. There are several true definitions.
Science. We would be like the process based in a scientific. I don't want to use scientific. The process to identify and certify or confirm the information in a. I don't want to use scientific way. I don't know how you call it in English. I got it in Spanish very clearly. In a structured. Like the scientific. No, sería como you speak clear Spanish. Okay.
No, but let's write it down.
The orderly fashion way to. Yeah, it will be like the science to gather data in a orderly, readable, understandable way. I don't know. I'm just throwing it out.
Mm-hmm. Okay, perfectly fine. Some other aspects or definitions.
It's to create and to test hypotheses based on data.
Mm-hmm. Also valid.
I don't know. Is it to get data and transform data into information?
Mm-hmm.
Research? I mean, data is data unless it is made into something actionable. So,
like for example, artificial intelligence. So now, what the thing is, it sounds always like something new. It's something very just out of it is there just for 1 or 2 years. But recently I was reading a news article that's actually not true. Data science, and maybe it was called before. It was already there for a long time. And it's kind of it started like trying to get with artificial intelligence and machine learning, for example, trying to get a data set or kind of a basin full of information, and teaching a machine how to interact, how to use this basin of information, how to make kind of a logic sense to it, so it will produce an outcome which is useful, or at least in a sense.
Okay, so thank you all for contributing. So there is a lot of aspects and they're all relevant, but obviously it's been so much on the news, we've all read so much about this, that we kind of feel we should know, but it's so unclear, it's not really there. Before we uncover, maybe ask you this question: what is machine learning? You've already thrown it into the room.
Yeah, like for example, there's this. I'm not sure if that's true, but that probably sums with it as well. And if I'm, for example, on Samsung tablet, all other tablets as well, you can make advertising here, but you can take a pen, you can write down like in your own kind of way. And some people have a really wonderful kind of way to write, and you can read it clearly. Other people, maybe like me, it's really hard to read actually what I was writing. So, but it's still, when I'm writing on the tablet, it still functions. So in the end, the tablet knows what I'm writing. The question is, how does it do it? And they're making it like this, that they're having, for example, writing down a 9 in a lot of different ways, or scanning them. So scanning them, so the computer has kind of a lot, hundreds, thousands, or maybe even million ways how to write a 9. And then if I'm writing a 9, he's going through all those examples till he kind of has something which is going to basically match up with my written 9. And then he knows, okay, there's a 9. Because actually for a computer it doesn't make sense. Like a 9 is just something, it's just a kind of form of a pixel. That's how he basically knows then what I was writing. It's just copying it.
We will actually go into this in a little bit with a video, and we will get into the brain of a computer and understand how a computer thinks. On a concrete example. So we can, let's just say for now, that machine learning is the technique that computers use to do data science, or to get sense out of data. So this is also not like the one and only definition. And data science is a very old science. You can actually say that the Babylonians already did data science when they were collecting information about taxpayers. And, so it is a way of storing, handling data, of making it accessible, and of making in the end sense of it. And how to make sense of it, this is when we get to other topics. Also to this very big buzzword topic, artificial intelligence. This is meant to have an artificial and not calculated way to make sense of this. So it means we don't program a machine as we used to in the past in a descriptive way. We say, hey, if I give you 2 plus 2, you add it, this is a mathematical formula for adding numbers, and then we always know it's 4. So what we do is we create a machine that programs itself, and then it does something. And we don't really know what in the end it does, because we haven't programmed it. And that's why it's called artificial. And this making sense of something can be making sense for us, or it cannot be. Maybe you've heard of the two chatbots that starting chatting with each other and developing into having their own language and using, in the end, very strange patterns that the humans put the plug. Yeah. So let's just have this for completion. Artificial intelligence, I wrote, computers program themselves to be suitable to make sense of data. Right now, we are at the stage where this is very task specific. Like, tell me what is on the street. Is that a passenger, or is that a lamppost, or is that a car, or whatever? And the aim is to get to a more general artificial intelligence. And right now, I'd say for 1-2 years, research is starting up to create AI that itself creates AI. And that is also something I'm working on. So if you're interested in that, we can later maybe have a talk about that. But that is also something that is really interesting because it will exponentially speed up this development. And the human brain will not be the direct bottleneck anymore. Okay, so now I will show you, as I promised, a video about a concrete topic on machine learning. So it's a very specific task that this computer later needs to do. And the task is to understand a handwritten number. Before, it's just pixel information and no sense. Only human could read a 9 in 1,000 different shapes, still as a 9. But computers, until recently, or actually until 30 years ago, but that's another thing, could not understand it as a 9, for example. So, and this video, we will not just watch it and be in the cinema. It's gentle, but still interactive. So we will have a lot of breaks and pauses. Maybe we will not even finish the video. We will just try to get meaning and our own personal connection to what is happening there. Okay, are you okay with that?
No.
No, you're not? I'm open for suggestions. I'm honest, I'm serious. Yeah. We also have speakers, right?
Yeah.
But then it must have smelled like the entire day, the entire week.
Smells like New Year cheese.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly.
Take the moment and appreciate what your brain is able to do.
I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. the particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future.
Okay, I think we have to do one more methodological thing here. So whenever you have a question, you want time to think, you want me to pause, then please just raise the hand. I will always be watching you, so I can always stop it. If I don't see you, just yell or make yourself heard that we can stop it. And the second thing, neural network, I was not explaining that, but we can think of our brain as a network of a lot of neurons, and in many areas of artificial intelligence, not all, they use artificial neural networks, which is computer programs that mimic the neural network of the brain, but this video will also cover this. Are you okay?
What I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing, not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network, quote-unquote, learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many, many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants. But in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But
So that all you don't really need to know and not need to remember. The message here, it's a general way, a general introduction into an artificial neural network, and they all work like this. They have different layers, they have the different nodes that are the representation of a neuron, and they, in the end, lead to a decision. In the end, this A and N, the artificial neural network, will give a prediction. What I have seen here is most probably a 9.
But one question.
Yeah.
What are the nodes basically doing? Like, in the end, there's a decision line, so every layer makes a decision and trying to basically exclude other possibilities. But how they're working, or is that to?
It will be covered in some way, but we will, right now, if this is the question, each node or each neuron is basically a function. It's a mathematical equivalent to a function. So it has parameters, which is the input. In this first layer, the input is the light intensity. Between 0 and 1, it's a normalized value. 1 is completely white, 0 is completely black, or something in between. And that is the first input number that gets into the function. We can think of it f of x, right? So x is the input, and then y, the solution, if we put x in the function, is the output. And a neuron works like that, that it sees how much input is coming in, and then it does the calculation, and then it gives something out. If that what is calculated is above a certain threshold. So for simplicity, let's say all the numbers are between 0 and 1, and let's say for simplicity, all the neurons have a threshold of 0.3. something comes inside this neuron, and usually it's many input numbers, not just one, but many. And then it does all the calculation with this long and fancy formula, and then in the end there is an output. And if this number is above 0.3, then this neuron will send data to the next neuron. It fires. If it's below 0.3, it wouldn't fire. So this is how it's done in biology, in artificial intelligence, in artificial neural networks. It's not really the case. It will always continue to deliver this information, but this is just for motivation. This is just the picture to understand. It accumulates the knowledge, the information, the number input, then it does the calculation, and then it will send the calculated information forward. This is also called the forward pass. And layers are just there to group the neurons. As you see, this is a so-called fully connected neural network. Fully connected because each node is connected to all the other nodes in the next layer. And if you take a middle layer, also sometimes referred to as a deep layer, it's connected to all the next layers, but also to all the previous layers, previous neurons. Sorry. So all those neurons, in this case, 784 neurons in one layer, because it's 784 pixels, 28 times 28. They are the input, and then also it gets outputted to all those neurons. So it's a massive amount of computation that's happening there. But in the end, each neuron is a function, and those functions change. And we will see in the video how. Because this changing of the function, that is what we call learning. Continue?
In its simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network.
Clear, right?
Pretty good.
Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which, for the time being, should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. And
I have a question.
Yeah.
When it's picking up these digits or shapes or whatever, is shape the only parameter it's looking to recognize, or also color?
In this example, it's not doing that with color, but it's also possible, obviously. So the thing is here, this is the meaning, right? So we want to get the meaning of this pixel input. And also when we have color, like the human brain, if it's not like a color damaged eye, can make meaning out of different colors. We can get more information, like is the dress in some color and whatever. So understanding the color is something a calculator can do, because it's an RGB vector, red, green, blue. I can tell you this is orange because it's in the range of orange someone defined. But to understand if it's orange and it looks like that, that's a jersey from the Netherlands football team. That is something that is more in the meaning area. So artificial intelligence and neural networks are capable of doing that. They are capable of taking a sound wave, yeah, which is in the end also just data, and then analyzing it through some layers, and in the end say, hey, someone said the word hello. And I wanted also to pause here for the questions that the moderator was just saying, or the speaker. Because how many neurons you have in a layer, in those hidden or the middle layers that make it a deep network, how many layers and so on, that is right now expert knowledge of those so-called data scientists, the people that create those ANNs. And this is quite complex, and this is why I said in the introduction that this is something that we right now try to automate as well, because that's time consuming. Right now, creating the right architecture is very difficult. And you can imagine, if you put just 2 neurons here or 2,000, will have a huge impact on what this network in the end will be capable to do. So the variety is just so big. And we want to reduce those error rates to have better ANNs, because we want the ANN to make less mistakes. I think there was, again, like just recently, an Uber car autonomously driving and hitting a woman and she died. I mean, it was super dark and so on, but still something went wrong, and we want to prevent that. And creating this architecture is the difficult part. If you ever read hyperparameters, this is those hyperparameters. It's the number of layers, the number of neurons in those layers, and so on. This is the so-called hyperparameters that define an artificial neural network. And in this case, it's just arbitrary. We will not cover why it's like that. We just know that's expert knowledge, and we know it's important to get from one neuron to the next. And right now we have covered the first layer, which is just a representation of how lit up the light sensor was. 1 for very lit up, 0 for black, or in between.
There is a lot of room for experiment with the specific structure here. The way the network operates, activations in one layer determine the activations of the next layer.
So he's talking about activations. Can someone just in one sentence define again what's an activation?
The higher the number is between 0 and 1, the more the activation is. So 0.7 is more activated than 0.2.
Yes, very good. So that's, you can also call it the state of the neuron. In each time, specific time we look at it, that is when before I told you that there is this function, and then it outputs something. This output, that's the activation, or the activation number. And in this example, it also stays between 0 and 1.
And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed it an image, lighting up all 784 neurons of the input layer.
So now it's an example of how the middle layers work.
Into the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents.
So right now this is almost correct, because in reality the A and N is never 100% sure. Here it would be 100% certain it's a 9 and 0% certain of the others. In reality this might be 0.82, and then what's close, maybe an 8, maybe a 4, maybe a 0, well, maybe a little bit of 7 and 4 could be also, and partly 8. So the network in the end makes the best probabilistic assessment, so to speak. It's kind of, yeah, it gives also the level of certainty. And here it says 100%, but it's not how it would be in reality, because that's not how the ANN works. Here you have also levels between 0 and 1, and also this in the end is all about probabilistics. It's again functions here, and it's data, it's numbers. So it's a lot of statistics and probabilistics. We will not cover the math here, but in principle it's functions, mathematical functions, and it's a whole lot of data.
And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents.
I just want you to think about this idea. There's subcomponents, and there is more than 10 subcomponents, and it's a combination of subcomponents. And if we have neurons, each representing subcomponents, one could be an upper loop, one could be a lower loop. And if, for example, we would have numbers that have 2 upper loops in our Arabic numbers systems, we don't have it, but in such a case, we would have 2 different neurons. One would be for a first upper loop, and one would be for a second upper loop. And if both are there, both would have a high level of activation, like 0.8, 0.9, 0.95, something like this. So when there is a 9, that would mean this would be lit up very well, the first neuron, and I think that's already it. And this is an image of what we think this layer in the network is doing. And so breaking it down into smaller and smaller pieces, or to going the other way, making it more and more complete. It's like in automotive, putting together the components.
That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits.
It's pretty smart, huh? Think about 10 minutes ago, 15 minutes ago, you were thinking, how on earth a computer can do that? That's so complicated, it's so complex. There is so many different ways to write numbers. And this is a way how you can break this very complex problem down into smaller problems. And this is what artificial intelligence is doing. This is what neural networks are doing. They're breaking down very, very complex things into more simple sub-problems and sub-patterns.
Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be?
Right? But then again, a loop is what? Round shapes, right? Consists of a few. So maybe that is the layer before. We have a few round shapes that are connected to each other. And then before we define what is round, and that is activated, right? So we pass it on to always the next layer.
Still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge. Or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether this is what our final network actually does is another question.
Do you feel now you have understood a basic idea of how this artificial neural network works?
Yeah.
Maybe let's make it a bit more practical here. What is, what do you think is necessary in order to make the A and N smart?
We need to have as many definitions of loops and these edges.
Very, very good point, yes. How can we do that?
By creating that many more layers.
Adding more layers.
But how would a neuron actually, how would we, like, let's take this layer here. Yeah? How would we know that we need that many subcomponents? How would we put the activation in here? Do we sit there and type all the numbers?
Automatically.
And how?
I guess we put all those the small tidbits in as many places for as many pieces that you can have of them, and then it picks up the most likely bit.
Do you tell each piece that looks like this is a piece of a possible loop that will possibly become a line? But all those pieces, little pieces in each layer.
In some very specific cases, this is even how it's done, but you can easily imagine this is very tedious work.
Yeah.
It's so much, because you have to think of all the possibilities that are there. And if you miss one, the network will not recognize it, get garbage out, say, hey, that's a 2, yeah, then you have a high error rate. So there's another way how to do it. It would be on the second video, but then we would have to stay past midnight. So let's rather have this covered here. So what we can do is those activations here, they are sometimes, or usually they are called weights.
Weights.
Weight. Maybe you've come across this, that artificial neural networks have weights. So you can also think of this as a weight between 0 and 1. So what happens when you usually train a network to be able to do that is you randomly distribute the weights. Just the network arbitrarily picks any number and puts it anywhere. And then you give it this number. What do you think will be the prediction of the network? Will it predict a 9? Or which number will it predict?
It's the first time that I give the network a number, it will be random, so it will be 5, 0.
Exactly.
So same probability for all, right?
over, like if you let it run 1,000 times, then yes.
Recognizes one correct one, then it includes like that.
So yes, it will be a random pick.
Yeah.
Let's say it says this is a 1. And then this is the output here. And then there is, of course, probabilities on the other numbers. But then we do something that we call supervised learning or agent learning, or we confront it with the so-called ground truth. So that is, for example, when a human being sits down and labels this piece of pixel information and says, this should be recognized as a 9. And then the network says, oh, I predicted a 1 with 0.7 and all the other probabilities for the other. I was wrong. And then it calculates a so-called error rate. Yeah? It can be a numerical result in the end. 0.8 of the probability was wrong here, and then it adds up, and then it says, okay, it should have been a 9. And then it does something that is called backpropagation. So it goes back all of those connections and corrects them a little bit. It says, hey, it should have been a 9. So when we see this, those should have a higher activation. So it increases the activation number here a little bit. Then it goes back and says, I don't know, yeah, it's those, right? So those should be a little higher. So it adds numbers here, but also it decreases the numbers for the incorrect choices. And also does this until it reaches the place here. And here it connects to the actual pixel values. So you know, if those pixels are lit up, it should activate those neurons more than those who are darker. And if you do this thousands, millions, billions of times, again and again and again, then the network starts to get better and better and better at recognizing, and in the end saying with a high probability, this is a 9. And this is what is meant when people say an artificial neural network is learning or is training. That is what a data scientist is supervising. He is controlling that the neural network in the end is capable of doing what it's supposed to do. And I told you in the beginning, neural networks are case specific. This neural network will be able to understand human handwritten digits. If we give it data of speech, it will give out probably a lot of crap, because it's not what it's supposed to do. Yeah, this is learning or training, and sometimes we hear the term a pre-trained network, and then we know it's a network which already had done the learning, where all the activations are in pretty good shape and will in most cases predict the right output. And also when you follow research on data science, you see sometimes that people try to find the best architecture, the best weights, the best activations, the best number of layers, number of neurons, and other hyperparameters. And those competitions happen between data scientists. They try to create better architectures, and in the end they measure something. For example, the word error rate. I remember when I had my first smartphone, the word error rate was around 20% in research. So it means every 5th word they got wrong. And that's why nobody used Siri or Cortana and so on, because it could just understand if you almost yelled at it in slow speech, like, please call that person, and then it got it sometimes right. And this word error rate was drastically decreasing in the last years. That is why now there is so much hype around this. Because, I will not tell you why, but somehow scientists found a way to create better artificial neural networks. And the word error rate dropped and dropped and dropped to 12%, 10, 5. Now we are around less than 2%, which is amazing. And now you can start really interacting and talking with technical devices, and they understand the context. They understand the meaning of the input of the sound wave. Do you want to continue?
Yeah.
A little bit? Okay.
That I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover,
So, I was always saying this is probably how it's done. Also, the speaker was saying this is an idea, because really, honestly, nobody knows what this artificial neural network is doing. They have tried to take layers out and other layers in and so on. So we have some certainty about how it probably works, and with pictures, it's kind of understood. But we are not certain because it's artificial. To us, it's a black box. Something goes in, something comes out. And that is also why there is a little bit of fear about it, because you don't program this, right? We had this idea to program each individual activation, then we would know. But that's too tedious. For complex tasks, people could not perform it.
So how do you monitor it, and how do you?
You don't.
So it's continuously.
You just see the
monitoring,
results
right?
and see if it's stupid or not. And that is also the point when a car will drive autonomously around the city.
Until
You
the other
can
gets
never
right.
be 100% certain it will never do a mistake. You can never be. It's not a complete and programmed system. It's always about probabilities, and sometimes there would be this one case which would be in a far edge, like so unlikely in a few situations, and then the choice would be something that we as humans would consider wrong. And it could happen, and there is never ever a guarantee that this will not happen. Because of the way this works, we will not know. We don't specifically give it the input.
So are you for autonomous or not?
That's another topic.
But it will happen only one time, because then you give the information back in the system. It was a wrong decision, and so the system says, okay, I have to learn the situation, and this mistake will happen never again. Perhaps another one, but this only one time.
It will happen less likely, and also if we are in a very complex system, like driving in the city, no situation is
Absolutely the same.
very exactly the same. Like if we describe something, we leave out so much information. Maybe we draw a comic, but the reality is always a little bit different. Even the sunlight might be a little bit different between the seasons. For us, we adapt to it. We will not even recognize, because it's every day. But for a computer, that means the light sensors react differently. And that's why, yes, it learns, but the guarantee is never there. And you've had a question?
So, are we able to set limits for this kind of artificial intelligence? And how could we do this? For example, with the autonomous driving. So,
maybe I give this question to the group. You have already some ideas.
I think probably autonomous driving, like the probability is still less risky than human beings driving, because they do wrongs.
that's for sure.
Yeah.
I'm sure that
Yes.
is.
And I think that it touches the question of ethics of artificial intelligence, and that's kind of a yeah.
That's a good question. Okay.
Yeah. So if we think of limits, we can think of it in this context just as error rates. So what we could do is it's actually like material science, right? You are also never 1000% sure that a piece will never break. but you can test it very, very thoroughly. And that's also what you can do here. So most probably there will be very, very strict limitations. Like it needs to make maybe 1,000 times less errors than a average human driver. Something like this. Maybe a system needs to be tested over 3 years and so on. The good thing about this is computers can do it, and they can run it in parallel, 1,000, million times. So they can test, I don't know, how many hours of YouTube videos are uploaded each hour? Like 200 years or something like this? Because the computing can be done in parallel. One driver can drive 1 hour in 1 hour. But here, you know, as much computing power as you invest, you can increase the actual learning. And that's good because a neural network can teach another neural network what it learned. If you have not one neural network, but several, and you give it the same data, and give it the same, and confront it with the same ground truth, with the same labels, still you get different neural networks. Because in the beginning, remember, all the activations were random. So they all had very different starting positions, and then they pick random pictures, like 9s, another one picks a 5 in the beginning. And then they randomly train, so they all get better, but in the end they are all a little bit different. And what you can do then is, it's one way to improve learning, is to calculate the average of all of this. Then you already in, like, there are scientific studies that usually you have much better results if you take the average of this parallel learning. This is one idea. So there is a lot we can do technically to improve it, but in the end, society and government should put hard restrictions on the error rates, on the time and the rigidness it is tested, and the different situations. If you think of age tests and so on, it's extreme situations, very extreme situations that a normal driver would not get there, but sometimes it happens, and then you are very happy that the car is even made for such extreme situations. And the same should be done for technology that is in the end making the car drive by itself.
What I'm asking myself is, like this error question, is it not going to be obsolete by itself? Because if I have kind of, let's imagine cars. I mean, cars, you know, on this planet, right? Building cars, like something like this. Every car itself is producing, basically, if it would be automatic driving, is producing every day kind of case studies, and every second, every millisecond. That's kind of a lot of data you're going to get every day regarding how many crashes there are. It's actually still a lot of positive things like happen, like, hey, I haven't had a crash yet, and that's basically a billion times around the world. So making everything connected, building up a data set where then the newer one, the later versions can start from the start and orientate themselves on, should actually solve the problem completely. Like, of course, there's still like this philosophical point of maybe there's an error, and statistically there still can be an error, but practically there's like none. Or is it doesn't work because there's kind of, I don't know, like a limitation to that? Or?
Very, very good point. So with more experience, with more exposure, the network learns.
You know, but the contrary thing is that the experience was gained on those situations which may not repeat exactly the same way.
Yeah, but for that very specific situation, you have the experience. And then this network is good with similar situations, right? But let's get to your last question. Is there a limitation? Like, we now learn this ANN example, how it learns, and we can imagine, okay, it's not just numbers, it's, you know, visual information in the streets, around the car. So let's say this car drives around. Will it improve this network, or will it not work? What do you think? You should be able to answer this question by now. Also, you were invited to join.
So you can all see it's stupid. If you don't know.
It's
No,
okay.
I don't know.
A lot
The only thing is, I feel that it probably will be able to improve itself, but only to a certain point.
Yeah, but
what could be a limitation?
But different, like, so let us cut right, and of course every situation itself, if you're going to break it super down, and every layer is kind of, everything is unique. But on a more macro level, it's not unique. Like, the Earth is not the universe. The Earth is kind of still like, the space, just, okay, you can build more buildings, but actually that's the space in overall looking like it keeps the same. So our conditions are actually kind of, they're not growing in such a potential way like such a system can grow. So such a system should be able to overgrow what kind of the limitations of the space we have.
Yeah, because our complexity is still limited.
Yeah, so it's not endless. Like the Earth is not like, has not the potential to offer endless possibilities, endless space. But such a neural network should, especially if it's learning like this and it can share the data, and the data can be stored. That's supposed to be a problem.
Okay, granted. So yes, the complexity is in the end also limited. It's a limited amount of data. It's huge data, but it still is not endless. It's not infinite.
Mm-hmm.
One point. And second point I'm telling you is it can learn, but it has a strong limit if we do it like this. Think about what I told you, how the network learns. You
The
remember?
weights.
Yes, but how does it, the initialization, and then it starts learning. How does it, there's one component we didn't talk about here. But
Supervisor.
What?
It's a human cube supervisor.
The supervisor, exactly. Yes, it needs the ground truth. If the car is driving around, there is no ground truth, right?
Yeah, but still, like,
or are you sitting there on the screen saying yes,
no,
correct?
Right or wrong, yes.
But I don't have to. That's the point. I do not have to sit there and push the buttons. If I have a lot of different cars who have more or less the same situation, they're going to tell this guy like, hey, listen, you made there a mistake, but actually, or like you made a mistake. That's how it should be. Like,
but how will it know that this was a mistake?
Supervisor will have to tell it.
Yeah. That's a limited factor.
Yes. So, but still there is a solution. This is very good that you came up with this. This example, I told you in the beginning, this is a concrete example that I'm showing you. But there is different ways of learning. This, what we have learned here, is so-called supervised learning because of the supervisor. There is another way of learning, there's a few more, but this example that you were bringing into the group here is a so-called reinforcement learning. We will not go into this. One example is already really good, so I'm quite proud of you that you followed until here. So this reinforcement learning is basically giving you two ways of feedback. One is, you still survived, and one moment, you're dead. Like in system speech, right? So reinforcement learning would be for the car, it uses a trained network, like a thoroughly tested, TÜV certified, whatever. So this is really good, and it's driving around. Each timestamp, each millisecond, each time frame it captures, it says, I'm still alive, I'm still on the ground, my sensors tell me my inmates are still alive, all is going well. So, and all of this is generating new data for a different artificial neural network, which is using this reinforcement learning. And this is new learning. And this can be shared with other cars. So it, in the end, will also affect weights in a neural network, but in a different way. It's slower learning, it has a lot more limitations because the ground truth, the supervisor, is really strict, right? It's very clear. No, I told you it's a 9, accept it. And the network, it will never question the supervisor. This is like the god for the neural network. It says, oh, it's a 9, so I accept it. In reinforcement learning, there is no supervisor, there is no agent. There is just, I survived, something in my systems is probably going wrong, the activations I had to get me through traffic were probably good, so I will enforce it a bit more, I will reinforce it a bit more, and other things will fade away. Then we get to the topic of forgetting. for getting different solutions. So this is why it's called reinforcement, but just as a general idea, it's possible, it will be done technically in a different way, and it will be slower learning. And this is strong and very expensive learning. Expensive because you need labeled data, and you need a human to sit there and do this. And there's, for example, a data set, a labeled data set called MNIST, where researchers at a university, they have labeled 20,000 handwritten digits. And this can be used, and it's used for many years.
Yes. In this example, God decided. So, and the supervisor is God, and he decided. But if I have 5 cars, we don't ask, or we will not ask God, we will ask my brother. So I have 5 cars, one car says it's a 9, the next 8 or 7, and we take the average. So I don't, the car don't need ask God, he asks his brothers, and the average of the meaning, right, wrong, 9, 7, is the solution of our 5 brotherhood. So we need not God for a supervisor. Our company or our group is the supervisor by themselves. Is a possibility to learn without the supervisor God or human factor. So the system takes always the average of the results. I ask my brothers, and we take, okay, 7, 6, okay, we say no, the average is 5. And next situation, average is 4. And so the system is learning by themselves because they ask also the whole group and not Godfather.
It's a very beautiful picture, and the principle is correct. But to tell you about the dimensions, the difference, if you have this in the context of autonomous driving, will in almost, like in very, very, very small number of cases, will be 7, 8, and 9. It will be 100 cars, I'm super certain it's 8. And then there is a few with 7 and 9. And then they adapt slowly. Not drastically, not radically, but slowly, but always and continuously. So reinforcement learning works in this context only if we have very well pre-trained networks. You know reinforcement learning from a lot of videos of, like funny videos of robots trying to do some stupid tricks on the internet. This is like robot learning is done via reinforcement. So you can imagine like the robot is walking, oh, mistake, oh, turning, trying. Or like those cleaning robots that go on the floor. Well, they're dumb, they're not learning, but they could be potentially, right? So, and this is reinforcement learning. And when you watch reinforcement learning in action, you hope that you have a safe environment where all this learning doesn't create too much damage. Yes, so that would be a very bad idea to use reinforcement learning from scratch for autonomous driving, because you need a lot of errors. You need to break your neck so many times before you kind of understand, I have to brake before the wall and not after.
Kind of Darwinism.
It's very brutal, yeah,
the best
and it's slow learning.
Yeah. It's called evolution.
Yeah. So,
Only
but
from
scratch, from the one cell organism that needed billions of years to create 2 cells, and it was always learning. So there's one video I could show you, like how reinforcement works. There's still time because I know it's already 7:30, so I want to kind of get to the end. Do you want to see a robot starting to learn reinforcement learning? It's a very, very simple example. So it's a machine that can only go left and right, and it has a pole on top. So the pole is not attached. It could fall to the side. And what the robot is trying to do is to drive left and right to balance the pole that it stays perfectly stable. But there is no like a flat platform. It's completely curved. So even if it's like a little degree to the left, for you to the left, it will start falling, and then the robot tries to balance. And if it's just like that, the pole already has acceleration and will continue to fall. So the robot, the driver, needs to learn how to catch the pole before it falls down. So it's, I think, 1 or 2 minutes.
Yeah.
Yes. Yes.
Alright, you made it curious.
You almost did half the video.
So do we have a browser? Can you help?
The video
Pole balancing problems. No, not pole dance. That's different videos. Pole balancing artificial intelligence. Reinforcement learning, the second one. Yeah, the second video is good.
This one?
Yeah.
What's going on, everybody? Welcome to another Deep Learning with Python and TensorFlow tutorial. In this tutorial, what I'd like to do is kind of show another typically, I mean, people are working with a bunch of examples really, really fast. And then if the pole itself, I think it's, what, 15%? Yeah, so if it, with just the cart pole environment. So the cart pole environment's really simple. The idea is that you'll start the pole, you'll have the control over the cart, and your only option is to move left or right. If you move basically too far to the left or too far to the right, it's game over. And then if the pole itself, I think it's what?
So this is episode 2000 that was shown in the beginning. Now it's episode 1000, which means 1000 iterations of learning. And so each iteration means they tried to create a network and it failed.
At 15%, yeah, so if it moves more than 15 degrees from vertical, you also lose. So
yes, so that is the condition. That is the error rate or the limit it has to go. So more than 50%, 15 degrees, that's not much, it already loses. So, and that is dead. I told you there is survival or death in reinforcement learning.
Usually the task is we're just trying to balance this pole by moving the cart left or right just a little bit. If you get a score above 200,
yeah, I think you already got the main idea. So that is another way. There is a few more other ideas of how we can do machine learning, how we can create this artificial intelligence. And I would like to finish now with the input, because I know it's been really, really a lot. How can I get back to the presentation?
Human learning.
Yeah. I'm so bad at that, so that's why I want the computers to help me. So, maybe let's wrap up a little bit. We've invested a lot of time in this video. We've paused a lot. We have seen how in a square of 28 by 28 pixels, 784, thank you, pixels, was translated into input neurons, the first layer of an artificial neural network that translated the light density in between, into a number between 0 for not lit at all until 1. Then it started in the next layer probably to group them a little bit. Oh, there's 2, 3 pixels next to each other and they're in a vertical line, so it's this small piece of shape. And then it did that many, many, many times for all parts of this 784 pixel grid. In the next layer, it tried to group them a little bit to get larger shapes. In the next layer, and so on, until in the end we said, okay, the number 9 is a circle in the upper part of the picture and a vertical line on the side. Or it could also have, you know, another, yes, for you like this, another half circle on the bottom part of the picture. That is what we call supervised learning in computer vision with an artificial neural network, and it's done with a supervisor with labeled data that is necessary, that is needed, and the process for doing that is in the beginning to randomly distribute those activations, those weights. Each neuron has one weight, and then by producing a lot of garbage and correcting it with the reality, with the truth. A so-called backpropagation goes through the network, slowly adapts the weights. So just remember, it's slowly happening, it takes time, but with millions and millions of examples, the network eventually gets really, really good and very precise. And now, or already for 2 years, artificial intelligence is better in detecting tumor cells than human doctors. They have less error rates than the humans who initially trained them. So with a lot of data, you get very, very good. So we could also come to the topic now of how this data should look like. You can probably understand if I have this and the human is kind of tired, says, oh, that's probably one. So if it gets wrong labeled data, it will be very difficult because the artificial neural network will never doubt the ground truth. So if you ever work with data and you want to use artificial intelligence for your applications, you have to remember, and now you know why, the data you give it to learn has to be perfect. And that is why sometimes you hear in the news you have to have qualitative data. This is so important. And also, I get a lot of, I work a lot with corporate projects with the KIT, and then usually the corporates say, oh, we have big data, we have so much data. And they have Hadoop clusters full of data. But how this data looks like? It's unstructured, and it's certainly not labeled. It's just huge tables of production data, of sensor data, and then if you go into the factory and look at it, yeah, 2 sensors are broken already for 2 years, but production, still running, so nobody cares. But then it's in the data, and if you use this data to do some machine learning with it, now you understand it will not work, or it will be quite limited. And also if you give a data of 2,000 sensors, and let's say even a dozen of the sensors are broken, then still, overall, the network will get very, very good. Because there is so much data to learn from, that those dozen sensors that are obviously very wrong, maybe they always predict 1. Let's say there's part in the database that no matter what's on the picture always says, it's a 1, it's a 1, it's a 1.
It will just eliminate that over a period of time.
Not completely. It will have a little bit of influence, but so marginally that in the end it doesn't matter. Wow, I'm really proud that I think if I look into your eyes, I have the feeling at least, or the illusion, that there is something of reason behind, and that you say, I understood why it's necessary like that. And you remember that was my aim, to give you an intuition of what artificial intelligence and data science is, and to know its limitations, but also its potential. The limitations, label data is expensive. The limitation, reinforcement learning, is very stupid and takes billions of iterations. But the potential, with a lot of data, you can outperform humans by a great factor, and you can parallelize all this development, and in the end, achieve higher than human performance in many areas. And now the research is going to how to connect those cards that they learn from each other. It's like the very, very beginning right now. It's not even clear how this is done most effectively and so on. And also another part in research is how can we get rid of this tedious stuff of deciding about layers and neurons and other hyperparameters to have a machine do that for us. Because in the end, it's thousands, millions of different situations. It needs to be modeled according to expert knowledge. This expert knowledge could potentially be activations in a neural network, right? And this is where the future will go.
And if you're interested to implement that in your organization, there is actually a center of excellence for analytics and big data in our company, and they give support So if you have potential use cases that you would like to discuss with them, just contact them. It's Guido Vetter, or just look for the Center of Excellence Data and Analytics. And they have the data scientists, they have consultants, they have a lot of people that are happy to help. So it's not a theoretical or magic. Actually, we implement that in quite a lot of areas within that already.
You were hiding quite well there.
Well, I'm not from the Center of Excellence, just promoting some colleagues.
So the last is a quote that I personally like a lot from also a very famous entrepreneur, Richard Branson. And he has a very extreme attitude in this, I know. But I think, especially in Germany, this is something we could use a little bit more. So do it, go out, get over your fear of talking to customers. You did that already today and you all survived. So, and this is also true for the next 999 steps to go. So just go and enjoy the process, enjoy your learning, enjoy being out of your comfort zone. Thank you. This is my contact. I will be here a little bit more for questions, but you can also find me in LinkedIn, Sing, whatever you want, and write me an email if you have any questions.
Well, thanks a lot, Ingmar. That was really fascinating, and you were fascinating also, swallowing and digesting this heavy intellectual load after such a day. And of course the question arises now, what has this to do with what you are up to in your startups? And we decided to play a little freestyle from here. So Ingmar would be available, of course. So he has some examples. We could arrange a discussion. Or we could play individually, that you just kind of collect around the table. Who still has some like curiosity to go on like this? So just give me a hint. So what are you up to? I completely finished up, or is it are you some curiosity and energy left? It's all fine.
Maybe after a short break.
It's just the chance, and you can use it as much as
individual.
Yeah, I would ask him some stuff, but I'm pretty sure he has other things like other people with interest.
Yeah. So any objections that we kind of close the common circle finishes, and who still wants to get into a conversation with Ingmar's, of course, heartily invited. Alright, so then, of course, one important message. Tomorrow we meet here, again at 9 o'clock. We start shortly with an introduction and head into the day tomorrow. Tomorrow is prototyping day. You're unleashed to build something. See you tomorrow.
See you tomorrow.
Das ist ein schönes Schlüsselwort. Wenn man sich so überlegt, wenn es wirklich funktioniert mit der Kommunikation, dass das System untereinander so auch so lernen kann, dann fehlt es ist halt wirklich im Prinzip.
Einer sagt A, der andere sagt B, und dann sagt deswegen habe ich aufgeschrieben, ich kann auf diesen Durchschnittswert gegen diese Meldung, also das sollst du das alle hier praktisch zurück, das ist Kommunikation.